Welcome to EET 260 microcontroller applications. And we're going to talk about light sensing today. And this whole confusing mess you see over here, we'll go device by device in there and kind of discuss what all these different devices are. The very first device that we will discuss is the venerable, moribund cadmium sulfide light-dependent resistor. And you can see that described here. There's a little substrate here with some sort of serpentine conductive path on it, and that path has cadmium sulfide in it. And the cadmium sulfide is affected by light. Its resistance is affected by light. The only problem with that being that cadmium is one of those elements that is proscribed. That is, it is prohibited. Is the right word there. Under the removal of hazardous substances worldwide effort, the ROHS, or ROHS as many people call it, ROSE, whatever you want to call it, ROHS. And that device is really handy because it varies its resistance with light. So what we're going to do is we're going to turn on our meter here. We'll bring it up here, and right now we can see that this device is reading about almost 21 k ohm. Okay. Then we'll take a flashlight and we'll shine it on that device like so, and it drops down to 3 k ohms, and or even less, and as we pull away and shine the light from a different angle so that it's not as intense, you can see that the resistance goes up the less light that falls directly on the sensor. Now, the sensor is this guy right here, and so here's the sensor with no light. Let's do that again, see if we can get back to. There's the sensor with no light, and we're actually at 21K. And there's a little bit of light coming in through the shades. I have the room lights off and everything, but as we shine more light on it, its resistance goes down. Pretty easy to see the operation of that. And with your basic stamp, Board of Education or whatever you're using, you can measure some resistance using the resistor capacitor discharge timing. So that's one of the things that's doable there. The rest of the sensors I have are photodiodes and phototransistors. So let's talk about the next one, which is this BPW. So it's Bravo Papa Whiskey 34 Sierra BPW 34S photodiode. And in that case, that device is right here. And I have uploaded the data sheets for these items to the Week 5 Blackboard Learn site, even including the light dependent resistor, this photodiode, and some other devices. And what we're going to do now is we're going to look at the circuit we have here, which is we go from 5 volts through a 100 k ohm resistor through a reverse biased diode here, but you see the symbol with the 2 arrows pointing in. That indicates that this is a photodiode. Now, if a diode is reverse biased, the only current that will flow in this reverse direction, this reverse direction through the diode, that is, some people call it leakage current. Pardon me. Its proper name is saturation current, although it doesn't mean saturation in the sense that we sometimes think. But it is the current that thermal processes dominated by Boltzmann's law. Thermal properties in here where charge carriers that shouldn't be going in that direction because of some thermal energy and quantum mechanics and a bunch of other magic potions, there's a very slight current that flows there. So I'm going to clip one side of our meter is on ground. The other side I'm going to bring around and clip here on the junction between. This is the BPW34S photosensor. This side is the anode. This side over here with the red clip and the 100K resistor going to +5, that's the cathode side. So right now we have almost no current flowing in this thing. If we look at our supply is 4.9798, and we're getting 4.79, so about 0.2 volts dropped across a 100k ohm resistor, and that's like 0.2 volts dropped across 0.1 meg. So we probably have 2 microamperes flowing through that circuit right now. Those 2 microamperes are just due to a little bit of ambient light in a late winter afternoon room with no lights on and just some light coming in from outside. Now, the way these photodiodes work is that this resistor is reverse biased, so you don't get much current. But if photons come in here and strike the actual PN junction of this diode, they will give energy to charge carriers which otherwise would not flow in this reverse bias direction. They will give energy, and the charge carriers will flow. They'll pick up the energy from the photons, absorb it. It gives them enough energy to flow against the direction of the diode, and hence we will have increased current flow. Now, if the current flow increases, that'll mean there'll be more voltage dropped across the quote-unquote dropping resistor here, and less voltage will appear across the reverse bias photodiode. So I'm at 4.8 now. If I come up here with a light and begin to shine it on there, you can see that the voltage, well, now this is the problem with this thing, it blanks out. So I'll try coming over here. As I shine this on there, you can see we've actually gone negative in voltage, in unreversed bias this so far is to read a negative voltage. But if I move this away far, let's see, can I move it away without blanking out my meter? Right now I'm at about 3 volts, and I'm moving away. I'm getting back up to 4.79 volts like we had, and there we are, just back to normal. So there you can see that a reverse bias diode, where the PN junction is actually exposed to light, can conduct in the reverse direction, and of course its chemistry is optimized for this purpose, if light shines on the diode itself. Okay, now if we wanted to, let's see what would happen if I take out. I do not know if this is going to work, so it's a little riskier. I'm going to take out that photodiode, and I'm going to put in this diode, whose cathode is represented by that black bar, and I'm going to put this thing in this location here. Now that's a reverse bias diode. I'm going to put our voltmeter on there, and let's just see if a silicon diode will conduct any differently. It says, boy, it's not conducting very much at all. It's maybe a fifth of a microamp there. If I flood that diode with light, let's see. All I can tell you is we didn't move very much. Yeah, we didn't move at all. So a regular silicon diode is just its chemistry does not promote absorbing photons at the wavelengths we can produce here. I could try using an infrared remote and shining on it and seeing if that will do anything, but it does not appear to. No, it really doesn't. So much for that experiment. A regular PN junction silicon diode in a glass case will not absorb photons in any of the frequencies we can generate here. Now I'll stick back in the our original photodiode. And reattach our voltmeter. And we go back to that kind of a reading. And if we shine light on it, the voltage goes down. I think you saw 4 volts there. I'm seeing about 2.4, 1.6 right now. Sorry for the lighting. It's just, I can try to change the black level of the light or the brightness like that, and you can almost make it out. You might have seen, yeah. Now I'm actually going below 0 volts because I'm flooding this with so much photocurrent that I'm generating a voltage about 3.9 volts, 0.39 volts. Okay, so there's one photodiode. Let's look at yet another photodiode. This one is called a TIL 413 right here. And yeah, let's see if we can get do an autofocus here and maybe sharpen this up. Now it's all black, and the reason it's black, it's meant to absorb infrared light. So it's a photodiode. I'm going to take this off of here. It's a photodiode, and it's described right here. It has a 1 meg resistor from, that says plus 10, but we're only using plus 5 today. Sorry about that. I think I already, I'll try to correct the ones I uploaded. The voltage isn't actually so critical, as this photocurrent, what we call IP here. Again, photons strike this thing, and more current than normally would leak through here. More current flows because the carriers, electrons, and the absence of electrons in the P and N types of this material actually flow, and they get their energy from the photons that strike the crystal lattice that makes up this PN junction diode. Well, that's all well and good, and however, if I got a little smaller flashlight here. So if I shine this thing on that infrared diode, not much really happens. I'm at 4.88, and I can go down to, I don't know, I thought I saw 4.81, but this is all visible light. It's not really infrared. All right, so I don't get much in the way. Oh, wait a minute. Perhaps I should connect my voltmeter to the correct resistor. Well, let's try it again. Now, my normal state here is 4.46 volts because there's probably some infrared energy in the room, maybe coming off of me, who knows. If I shine some visible light on it, it drops it a little bit, drops it down to 4.2, but that's really not much at all. Now, if I let's see if we can get enough infrared light out of this is a TV remote kind of thing, and I'm going to shine infrared at this thing and see if we get any change in voltage. Yeah, we got a little bit. We went down maybe 0.46 volts. Of course, this is this is 0.47 volts. This is intermittent. In other words, this is data that's being sent from the from this thing, and the data is pulses of infrared. I also happen to have an infrared LED right here, and that infrared LED is on right now. It has a dropping resistor here, and the way I can tell that it's on is if I turn on my phone and I set my phone to the camera setting. I think, and I may have to, okay. Let's see if I can bring it around so it's in the field of view here. Yeah, I'm gonna have to bring down the camera in brightness, and I might have to. I have set the mode on my phone. It's back to auto. That's the problem. So I'll set it to pro, and I'll change the white balance. And now, hopefully, you can see that kind of reddish purplish glow right there. That's an infrared LED. And it turns out that phones, you may already know this, phones can detect infrared radiation, within certain wavelengths or frequencies. Here's I'll try to do the remote here. Here's the get it down here. See, there's the remote control. If I turn it on and off, and of course there's the LED on here. If I remove if I interrupt the current to the LED, it goes off, it extinguishes, and if I re-engage it. So we have an infrared source in this LED right here, and I will bring the bring our brightness. I guess didn't need to bring it down. So we're still sitting here at 4.46 volts. If I bend the LED down so it's now pointing toward, see, our LED is now pointing toward our infrared sensor. We have swamped this thing with so much infrared that we are actually driving it below ground, which I'm not sure I can exactly explain. But at any rate, we are making it conduct like the dickens because we're bombarding it with infrared photons. Okay. And if I bring this up here so they're aimed up there, we go back to our normal level. If I disconnect this might have been our ambient source of IR. Yeah, I go up 400 millivolts, so that's not much. So now you've seen photodiodes, both photodiodes optimized for visible and photodiodes optimized for infrared. If I go back to the BPW34S, it's around 4.88 where it was, and I hit it. Yeah, that's right. We get a little bit of effect with infrared. I'm hitting it with the TV remote, and so we do see some photonic effect with infrared. Infrared waves are at a lower frequency than visible light, or that is also to say they are at a longer wavelength. The last direct sensing device I'm going to show you is a Motorola MRD 3056. So that's a I can't even think of what R is, but Motel Roger Delta 3056. I don't know why R isn't coming to my mind. But this, maybe I can get down here and look at it a little better. This thing is actually a steel transistor with a glass top on it. So I'm going to try to let this autofocus. And you can sort of see that it has three leads here. If I go, there's a lead over here, right there. There's a lead right here connected to a resistor. This is an emitter of a transistor. This guy is actually a base of a transistor over here, and he's not connected to anything. And this is the collector of the transistor. So we're using it like a photodiode right now. But if we look at the actual schematic of what we have hooked up, I'm going to go back up a little higher so it's not going to, we're not going to see it as well. But if we look at this circuit right here, there we go, a little better focus than we had. If we look at that circuit, we can see that the transistor itself, this is a bipolar junction transistor acting like a photodiode. And in practice, the collector base would, in a typical bipolar junction transistor circuit, the collector base would be reverse biased, and the base emitter would be forward biased. Now, since we have photons entering the transistor because it has that little glass lens on top, we could set this base lead so that the transistor is not forward biased, but maybe on the hair edge of being forward biased, or maybe even a little bit forward biased. In essence, this base wire allows us to inject electrical current into here, just like a transistor, And then the photons would take us, would add conduction, give us more current down here in the NPN emitter. And so we're going to measure the voltage out. And the idea of these photons striking the base region of the transistor, it's just like putting current in the base. If you remember, the transistors have a beta, or HFE if you use H parameters. But the amount of current that flows into the base, which usually follows and forward biases this diode. So the amount of current we put into the base is a fraction of the amount of current that flows down through the collector and out the emitter. So you take this collector current, you divide it by the base current, and you get a big number called beta. It's 100, 200 or something like that. And so now we have just a small resistance down here, but we're going to be able to generate enough current with our photons because this transistor is essentially acting as an amplifier for us. So I'll bring back the this guy, and bring up the brightness a little bit. We have our circuit hooked here with, we have it shows here over here 10 to 20 volts. We just have 5 volts connected to our collector. The base, as I pointed out before, over here is just hanging in midair. It's not connected. And then the emitter has a 100 ohm resistor to ground. So let's connect our voltmeter to this emitter, and right now it appears like we don't have very much current at all. We have, it's essentially zero current. So if I can locate my flashlight here, and I drive that down there, you can see we now have, we've gotten up to a volt. I've gotten up to, I put the flashlight, I got just about touching the lens, and get up to 2 volts, and as I pull away, it gets less and less. Here I am at 200 millivolts, 300 millivolts. And if I absolutely flood it with my cheapo Home Depot LED flashlight here, the voltage is, okay, that's not good. We lost something. Here the voltage is up to, well, I had it up to half a volt there at one point in time. Now I got it up to a volt. You can see. So that's pretty good, really, because if I can get it to a volt, or remember in this other case with the little pen style flashlight with a white LED, I got it up to we're at a volt now, and almost 2 volts. Well, if I get to 2 volts with 100 ohms, that's 20 milliamperes. In these other examples, we were doing, I don't know, we maybe are getting up to a milliampere or something, or we're still in the microampere range, maybe just many tens of microamperes. But here we get 2 milliamperes. That's pretty good gain, and a good device for sensing light. It could be used to trigger something in our circuits. Now I'm going to turn my room light back on, and we're going to talk about one last device. So the last device we're going to talk about is called an optocoupler. And there are a couple of variants of it, but basically one takes an LED, and they're very often infrared. So here's the circuit for an LED. Here's the symbol, I should say, for an LED. Wait a minute, sorry, my bad. There we go. So there's an LED, and in the same package we might put a photo transistor. Okay. And then in between here we have isolation. So there's no, okay, let me move the brightness down a little bit. Okay. So now there's no we have isolation here, which is great because you know, we put some current through here and it creates a light which reaches across to here and causes some current to flow here. So if I have you know, I can call this IP1 for photocurrent here, and I can call this IP2 if I like for the photocurrent there. And so this is nice because I can, without having a common ground connection or anything else, I can use a current in this circuit to create light, to turn on a transistor, and control current in this other circuit. In fact, you can even find these optocouplers, and we'll put the word here, optocoupler. You can find these, they have some that are linear. I happen to have one here that is not linear, it's just on off. And in fact, it's so this is a 5-pin dual inline package, 5-pin dip package. Is very common. And of course, now they would be probably a 6-pin dual inline package. And they would very often now probably be a 6-pin SOIC or SOT236 or MSOP of some kind. So you know, surface mount, but they still make these through-hole units. And so this is the basic operation of an optocoupler. Now, you could do something, if we look at the circuitry here, this, you might put 10 milliamps through here. That can easily be sourced by the output of a basic stamp or an Arduino, or any microcontroller can usually come up with 10 milliamps, and if it can't, a transistor can easily solve that. But over here, this circuit might control a transistor. You know, perhaps we have a resistor here. We might have a resistor there, and you know, you might use something like supposing this is a transistor, and we'll put a PNP transistor here. You don't have to, this is just one flavor of a circuit. And when the light shines here, this voltage right here will decrease. That will turn on our PNP transistor, because we'll conduct current over here to the ground on this side perhaps. Alright, and then this PNP transistor now can conduct current over here It could operate a relay or another transistor, or however you want to do it. Put a relay coil in here. Put our backlash diode in there. So here's our relay coil. And this relay, you know, this might operate off a supply. Maybe this is 40 volts over here or something. I don't know. Or, you know, this relay achieves a similar thing as to what this opto-isolator does. It has isolation between the input and output. So we might not even want to use a relay. We might use something like an SCR. Maybe we'll inject current. You know, maybe we'll inject current into an SCR. And this circuit over here, this circuit could be 600 volts. Okay, as long as we properly, you know, get the right transistor here and protect all this stuff. But the point is, whatever was doing the thinking over here and wanted to turn this thing on can operate off of 5 volts and never has to see 600 volts. You can easily get opto-isolators with 1500 volts of isolation, and you can get some with more. So that's an optocoupler. It's, you know, inside of this little 6-pin dual inline package, you can pretend, you don't have to pretend, it's really true. There's a light emitting diode, probably infrared if I remember, and a phototransistor, and there's actually a gap in between there, and they're used, so you can use light to communicate from one voltage or region to another. And this may be this might be some underwriter's laboratory decreed boundary on which there can be no galvanic conduction. Such things exist. In fact, they exist in many what are called medically rated switching power supplies. The pulse width modulation to run the power supply is supplied across the protected boundary by optocoupler. You'll see some of those. They just have the 4 pins, because, like in this case, we really only need 4 pins. The last thing I wanted to mention is there's another type of optocoupler. It's called a photo interrupter. And I'm going to not my best effort. And they look something like this. And one side of this, so that there'll be a couple of pins over here, and one side of this will have a photo emitter of some kind, let's just call it an LED, be it infrared or visible. So one side of these is an LED, and the other side of this contains a photodiode or a phototransistor. Okay, and there'll be a couple of leads over here for that side of the thing. Now, you know, if you're on a motion control machinery or something, you might have a fin on a moving stage, and the fin actually comes along and blocks the light here, in which case normally you might have this hooked up so that light is is being sensed going across here. All right, but maybe a spinning wheel with a hole in it, or like I said, a sliding fin on a stage, you know, that comes along and cuts into this path, turns it off, and gives a signal to the motion control electronics to maybe, you know, stop the thing at that point. Maybe it's reached the end of travel or something like that. So you know, I mean, I've built these things built these things out of 2 individual parts, and, you know, taken a soda straw or whatever and tried to, you know, kind of block out light and make it go across. I've even built I built a photocoupler with a neon bulb. This is a bulb with 2 electrodes filled with neon gas that will fire to around 72 volts. And on this side, I've put one of those light-dependent resistors. And the application was telephone ringing detection. Telephone ringing circuits use 90 to 120 volts at 20 hertz, 20 cycles per second. And at the time, we were not allowed to, and still true, you're not allowed to connect to a phone company circuit or really anybody else's circuit. And so we, well, I guess we did, because we picked up the ringing voltage here. But in order to, the ringing voltage would fire this this neon bulb 20 times a second. And we had a current limiting resistor in here. And so this would light when the phone was ringing. We'd pick it up here and go through a transistor circuit, and it let us know that a call was coming in and that we could activate whatever we needed to activate. So these optocouplers, as you've seen them, and photo interrupters. So this is called a opto interrupter, photo interrupter. You know, these are just great for motion control, where you want something to happen when something moves into place, or you want to watch the speed of a rotating disc. And we'll be talking about rotary encoders at some point here. But anyway, that's about all we have to say about light sensing and its applications. You know, with some of these sensors that we discussed, you could actually get a scale of how much light comes out. And that's great when you want to measure light intensity, maybe measuring the light through a blood sample to detect density of the blood, or you know, through a chemical sample to determine how much, you know, how dark it is, and therefore how much a certain chemical is in it, or, you know, measure how dirty water is, or maybe how dirty oil is from a lubricating system or something like that. So there's a place where you can actually measure the amount of light, but also you can just use light as an on-off digital control, And so, it's used both ways. All right, we'll be talking soon. Just wanted to do that lecture, and I will put some of these devices, data sheets, onto Blackboard as well. Okay, see you next time.